So as we move into section 4.6, we get to the point of the class where it kind of feels like we stop learning things for Calc 1 and we start sort of setting the table for Calc 2. I mean, it's not like there's a really clear delineation between what fits in a Calc 1 class versus a Calc 2 class, but I think what you'll see is in this section and the next few, we learn some things that might feel a little bit different to you. So fair warning. So as you hopefully recall, everything we've learned in this class was kind of based upon this idea of limits. Specifically, for Calculus 1, we studied limits at a removable discontinuity. The way to think about it is, you have some function and you're interested in the, loosely speaking, steepness of this function. The way we define steepness is by talking about the slope of the tangent line to a curve at a given point. So the steepness of this green graph at this dot is represented by the slope of the line in red. But how do you calculate the slope of the line in red? Well, you kind of don't, at least not directly. You instead pick a second, different point on your graph in green and connect that to the point at which we want to calculate the steepness. Connecting these two dots produces a different line, not a tangent line, but instead a secant line. Now, and this is where the jump really comes, if you consider a second graph, and on the y-axis of this second graph, we plot the slope of the line in orange, and on the x-axis of this second graph, we plot the x-coordinate of the second point that, along with the original dot that we're trying to measure the steepness at, defines a secant line. Well, we can kind of get an idea of what that would look like. This second dot over here produces this really steep line. So I don't know, maybe this x-coordinate corresponds with that second dot. It produces a steep line, so I want a big height to represent that steepness. If the second dot, instead of being right here, is, I don't know, over here maybe, then my secant line would be horizontal. So the slope of that secant line would be 0. So when my second x-coordinate is somewhere over here, the slope is equal to 0. The height of this dot is 0. At points in between this point in orange and this point over here that produced a horizontal secant line, the slope of the secant line would always be positive no matter what number you pick over here. You can kind of see your different secant lines. And we don't know exactly what those heights would be, but importantly, when the second point is exactly on top of the first point that we're trying to measure the steepness at, our secant line is undefined. At this point right here, represented as this point on this graph, we have an open circle, a removable discontinuity. The secant line has a defined slope when the second point is any x-coordinate you want other than exactly the same as the first x-coordinate. If I created a graph that plotted the slope of the secant line as a function of the x-coordinate of that second point, it would look something like this. I don't know exactly what it would look like, but frankly, it doesn't matter what it would look like. The key thing to note is it would have this removable discontinuity. For that reason, it's really important to be able to evaluate limits, because the height of this removable discontinuity ends up representing the slope of the line in pink that we're trying to figure out all along. Figuring out the height of the removable discontinuity, how high is this point that's not even really on this graph, is a really tricky question, and it necessitates this idea of limits. And it ends up being completely fundamental to everything you do in Calculus 1. In Calculus 2, it'll turn out you're again concerned with limits. However, there'll be a different type of limit. You'll be less concerned about limits at removable discontinuities like we see pictured up here, and instead you'll be concerned with limits at vertical asymptotes and limits at infinity. And those are the two topics that we're going to talk about in 4.6. The good news is both of those things are topics you've essentially learned with different language in a pre-calculus class. And really they all kind of hinge upon your understanding of the graph of y equals 1 over x. There's a few more kind of axiomatic facts that I want to go over in this video, but the main one is just understanding this y equals 1 over x, because that will be integral to everything that we do with limits in 4.6. So let's start by looking at the graph of y equals 1 over x. It's what's pictured down here in blue. You can kind of verify to yourself that this makes sense. When the x-coordinate is 2, for example, y would be equal to 1 over 2, in other words, 1/2. So the height would be 1/2, which looks about right, because if 2 is here, 1 is right here, so 1/2 is right here. Note over on the right side of my graph, the heights are always positive, and that's because on the right side of my graph, the x-coordinates are always positive, and 1 is a positive number, and a positive divided by a positive is always positive. When the x-coordinate gets larger and larger when I go off to the right, this fraction gets smaller and smaller, and that makes sense as well. If you think about this fraction as division, if you have 1 of something and you're dividing it up amongst, I don't know, 100 different people, each person's going to get very, very little. When x is equal to 100, y is really, really small, damn near 0. If you continued this graph to picture x equals 100 way out to the right, you'd correspond with the height that's really, really, really close to 0. On the left side, we kind of have a mirror image of the right side, a fact you could probably talk yourself into. The only difference is now we get negative numbers, which makes sense because a positive number, 1, divided by a negative number, the value of x over on the left side of the graph, is going to result in a negative number, all these negative heights. That's all the basics of this graph y equals 1 over x, but perhaps the most important feature of this graph I haven't even talked about at all, and that's the fact that we have a vertical asymptote at 0. The height of this graph is not defined when x equals 0. And that makes sense because 1 divided by 0 is undefined. You can't divide by 0 in math. This graph has a vertical asymptote at x equals 0, and if you had to describe its end behavior, in other words, the behavior of the graph when the x-coordinate gets really, really large or really, really large negative, in a pre-calculus class you may have said something like, as x tends towards negative infinity, y tends towards 0, and as x tends towards positive infinity, y tends towards 0. When I go way to the left, the graph approaches a height of 0. When I go way to the right, the graph approaches a height of 0. In other words, we have a horizontal asymptote at y equals 0. In pre-calc class, you spend a lot of time talking about the end behavior, both of polynomials and rational functions. And hopefully at some point you learn how to describe end behavior mathematically, and the way you can do that is either with this kind of mathematical sentence, or equivalently, by noting the existence of a horizontal asymptote. Well, this isn't a pre-calculus class, this is a calculus class. So we're going to talk about things slightly different, but really all we're going to do is capture these same ideas we've already talked about. We're just going to do so using limits. Because limits, just like they were the key to unlocking Calculus 1, will end up being the key to unlocking Calculus 2. What kind of limits are we interested in? Well, here's a few. First, I want you to understand what is being asked if you saw this mess of symbols right here. It might look really complicated with infinities floating around and stuff, but I think if we kind of parse it all out, it won't be that bad. We're evaluating a limit, which is what the LIM stands for, just like it did before when we saw limits. And this time it's the limit as x approaches negative infinity. We're not used to seeing infinities in here, but conveniently they act probably just how you would expect them to act. If you kind of picture your number line here, all your different x values, and kind of imagine a positive infinity way out on the right and a negative infinity way out on the left, then all of a sudden this makes a lot of sense. It's just asking you what happens to this function 1 over x when the x-coordinate approaches negative infinity. In other words, when I go way out to the left on the graph. This question right here is identical to the end behavior that we described in a pre-calculus class, specifically this first line of the end behavior. Instead of writing as x approaches negative infinity, y approaches 0, what we will say is the limit as x approaches negative infinity of this function 1 over x is equal to 0. Similarly, instead of saying that as x approaches positive infinity, y approaches 0, you might be asked the limit as x approaches infinity of 1 over x, and your answer there would be 0 as well. This time because of this second line of our end behavior. This statement involving limits means the exact same thing as this first line, and this statement involving limits means the exact same thing as this second line. But that's not going to be the only use of limits describing end behavior. This really important characteristic about the vertical asymptote can also be described using limits. The limit as x approaches 0 from the negative side of this function 1 over x. Remember, from the negative side means the hiker is coming in this direction. So maybe for this question right here, you're sort of picturing a hiker walking, I don't know, somewhere out here, getting closer and closer to an x-coordinate of 0. What's being asked is, what does the height of this hiker approach as this hiker gets arbitrarily close to 0? Well, this hiker just keeps going down, 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 kind of down this infinitely steep cliff. Their height doesn't approach any number. It gets infinitely far negative. How can we capture that idea using limits? What we do is we say that the limit as x approaches 0 from the negative side of 1 over x is equal to negative infinity. I mean, that's probably the answer that would make sense. It wouldn't make sense to put any numbers in here because this graph goes down as far as you want it to go down. But this idea of using infinities, or negative infinities in this case, as answers to questions is a little bit foreign. When we were dealing with removable discontinuities, the value that the x-coordinate was approaching was always a number, not some concept like infinity. And the answers to these questions with removable discontinuities were always numbers, not these concepts like infinity. The limits that we care about for calculus 2 will be in some way related to infinities. Either they'll be infinities in the questions, like you saw in these first two examples, where essentially all we're doing is describing end behavior, or the answers themselves will be infinities, which come into play when we're talking about a vertical asymptote. What's the limit as x approaches 0 from the positive side of 1 over x? Well, remember, the positive side means the hiker's coming in this direction. The hiker's getting infinitely close to 0, but now the hiker's coming in on this trail. The closer and closer to 0 we get, the higher up this hiker goes. This hiker never stops. This hiker gets infinitely high. The limit as x approaches 0 from the positive side of 1 over x is equal to positive infinity. These four statements make sense to you in the context of limits in this graph that you see. You have a really solid understanding for the foundations of the limits we'll be evaluating for a Calculus 2 class. At this point, you might be like, whoa, this is way easier than what we did with removable discontinuities. I'm going to love Calculus 2. It must be much simpler. Well, unfortunately, no. We're just kind of working on the foundational concepts for Calculus 2 right now. But if you find these foundational concepts pretty intuitive, that's really good, and it probably speaks more to your understanding of limits from Calculus 1 than Calculus 2, so you should be proud of yourself. The bad news is this isn't all the fundamental knowledge that we'll need for Calculus 2. There's a few more important facts, but I think they'll follow pretty immediately from what we've done already. We're going to continue to evaluate limits as x approaches infinity and negative infinity, but now we're not going to just look at this graph 1 over x, we're going to consider different graphs. Which graphs? Well, let's start out with x to the n power. The x is approaching infinity, but wait, what's happening to the n? N is just some positive integer. You don't know what it is. So in your head, maybe think n is 5 or 6 or 10 or something. But n is not changing. N is some fixed positive integer. If it helps, think the limit as x approaches infinity of x to the 4th power. Sure, that'll work. If your value of x here is getting really, really, really large, and you're raising it up to the 4th power, what's going to come out of that machine? Well, something really, really large would come out of that machine. Exactly. If that makes sense, you understand this limit. The limit as x approaches infinity of x to the 4th power is infinity because the larger the base gets, informally speaking, when we raise it up to the 4th power, the larger that expression is going to be equal to. And there's nothing special about the 4th power. The limit as x approaches infinity of x to the n power for any positive integer value of n is always equal to infinity. Just think large numbers raised up to positive powers give you really, really large numbers. Sure, it's all super intuitive. Gets a little bit harder if we consider x approaching negative infinity. We're again assuming n is a positive integer, so maybe you're thinking, I don't know, the limit as x approaches negative infinity of x to the 4th power, or the limit as x approaches negative infinity of x to the 3rd power. But now we have to be a little bit more careful. Because if x is approaching negative infinity, you're kind of imagining, I don't know, negative a billion or something. Negative 1 billion to the 4th power, because a negative times a negative gives a positive, approaches positive infinity. But negative 1 billion to the 3rd power, for example, ends up giving you a negative, because a negative times a negative is a positive, and then that positive times another negative yields a negative. More generally, the limit as x approaches negative infinity of x to the n power is equal to positive infinity if n is even. But if n is odd, that's not the case. In the case where n is odd, the limit as x approaches negative infinity of x to the n is equal to negative infinity. We didn't care about whether n was even or odd when x was approaching positive infinity, but when an x is approaching negative infinity, it ends up being really important, as hopefully you can see from these examples up here. A couple more little facts. What if instead, considering what happens when the base of these exponential expressions approaches infinity or negative infinity, what if we instead considered what happened when the exponent in these exponential expressions approached infinity or negative infinity? Well, much like this second case here, the answer is it depends. Specifically, it depends on what your base, a in this case, is equal to. We're going to consider two different cases. We're going to care about when a is a number greater than 1, and we're going to care about when a is a number between 0 and 1. We're never going to care about when a is equal to 0, because if a is equal to 0, this expression equals 0 no matter what the value of x is. Nor are we going to care about what happens when a equals 1, because if a equals 1, this expression is equal to 1, because 1 to any power equals 1. And things just aren't that interesting. We're also not even going to consider what happens when n is a negative number, because that ends up causing all sorts of trouble. The reason it causes trouble is because if this exponent is a fraction, we end up involving roots. And taking square roots of negative numbers, for example, cause all sorts of trouble that we don't want to get into. So for our purposes, we're only going to consider when a is a number greater than 1 or when a is a number between 0 and 1. So what is the limit as x approaches positive infinity of a to the x power if a is greater than 1? Well, you might have a guess already, but maybe it'll help to think about a more specific example. What if we considered the limit as x approached infinity of, I don't know, 2 to the x power? Well, x is some really, really large number, and 2 raised up to some really, really large number is going to be some really large number, right? 2 to the 5th power is 32, 2 to the 6th power is 64, 2 to the 7th power is 128. As we continue to make this value of x larger and larger, what this expression is equal to gets larger and larger. The limit as x approaches infinity of 2 to the x power is equal to infinity. However, as you may have guessed, we're going to get a very different answer if our value of a is not greater than 1. So maybe, I don't know, think about a being equal to 1/2. What would be the limit as x approached infinity of 1/2 to the x power? Well, again, you're thinking about x is a really, really large number. So 1/2 times 1/2 times 1/2 times 1/2, a really, really large amount of times, loosely speaking. Well, each time you multiply by 1/2, you cut the value of that product in half. So if we continue to cut things in half over and over and over again, we end up with less and less and less, informally speaking. We end up with the number arbitrarily close to 0. The limit as x approaches infinity of 1/2 to the x power is equal to 0. And similar logic tells us that the limit as x approaches infinity of a to the x power, if that a is in between 0 and 1, is equal to 0. I got 2 more cases that I want to consider before I end this video, but what you'll see is they're pretty similar to the 2 that we just did. We're again considering the limit of a to the x power, where a is either going to be greater than 1 or between 0 and 1. But now, instead of letting our value of x get arbitrarily large, in other words, approach infinity, our value of x is going to get arbitrarily large negative, in other words, approach negative infinity. So what's the limit as x approaches negative infinity of a to the x if a is greater than 1? Well, again, maybe we need an example to think about. Let's consider the limit as x approaches negative infinity of, I don't know, 2, sure, to the x power. Well, the trick for this one is to remember what it means for exponents to be negative. A base raised up to a negative exponent is the exact same as 1 divided by that base raised up to the positive exponent. For that reason, the limit as x approaches negative infinity of 2 to the x is going to be the exact same as the limit as x approaches positive infinity of 1/2 to the x power. Wait, what just happened there? Think about a really, really large negative value of x here. That's going to be the exact same as 1 divided by 2 raised up to a really, really large positive value of x for this reason. So this expression is the exact same as this expression down here. But because 1 raised up to any power is just equal to 1, this expression down here is equal to this expression up here. So these two must be equivalent. Why is that important? Because this expression on the right, I already know the answer to. A minute ago, I figured out that that limit was equal to 0. So for the same reason that the limit as x approaches infinity of 1/2 to the x power equals 0, the limit as x approaches negative infinity of 2 to the x power equals 0. Much like the limit as x approaches infinity of a to the x equals 0 when a is in between 0 and 1, the limit as x approaches negative infinity of a to the x power when a is greater than 1 is equal to 0. To make sure that makes sense, figure out what this limit's equal to. The limit of a to the x power, where a is some number in between 0 and 1, maybe think a is 1/2, just so you have an example in mind, if that x is approaching negative infinity. Well, again, we could take advantage of some work that we did prior. The limit as x approaches negative infinity of 1/2 to the x power is the exact same as the limit as x approaches positive infinity of 2 to the x power. Wait, why are these two things equal? Well, because when you have a fraction raised up to an exponent, you can raise the top of that fraction to the exponent and then divide that by the bottom of that fraction raised up to the exponent. So the limit as x approaches negative infinity of 1/2 to the x power is the exact same as the limit as x approaches negative infinity of 1 to the x power divided by 2 to the x power. But 1 to the x power is just equal to 1. So it's the limit as x approaches negative infinity of 1 divided by 2 to the x power. But remembering that negative exponents mean take the reciprocal of, this expression is equivalent to the expression that we have over here. The limit as x approaches infinity of 2 to the x power is something we've already figured out. We concluded earlier that that's equal to infinity. So since this limit is the same as this limit, we know that the limit as x approaches negative infinity of a to the x power when a is in between 0 and 1 is going to be equal to infinity. I think there's 11 facts we've gone over in this video. We have these two, these two, these two. this one, and then these 4 up here. And you can memorize all 11 of those if you want. It wouldn't be that hard. It's just a bunch of infinities and zeros and negative infinities. But I'd encourage you not to, because understanding what's going on, why these limits are equal to what they're equal to, will serve you much better going forward than just having these facts memorized. So maybe spend a little bit extra time going over these and really making sure they all make sense to you before you move on to the next video. In that next video, we'll work through a bunch of examples, which will hopefully help all this stuff, which is a little bit on the theoretical side, sink in a lot deeper.